Thank you for the introduction. So can you hear me? Great. So welcome to everyone. Today we'll present you our work done with the co-author and advisor Michael Pradel. We are from the University of Stuttgart in Germany, and it's entitled Bugs in Quantum Computing Platforms, an Empirical Study. So let's start. So I want to introduce a little bit of motivation and background to this work. So in the past, the introduction of multi-core hardware increased the risk for a new kind of bugs, the concurrency bugs. And here we have a combination of two key elements, so the introduction of new type of hardware and also a new computing paradigm, which led to the question about the introduction of new types of bugs. And similarly, nowadays, with the introduction of the quantum computing paradigm and the relative hardware, we have a similar question. So whether we have new kind of bugs arising because of this new pair of technology introduced. So this is also the goal of our work, to investigate whether we have new kinds of bugs happening in the wild due to the introduction of quantum software. And the outlook here is to better inform and guide future quality assurance research specific for quantum computing. I want to be precise that our focus will be on this part. So we have the physical layer at the bottom, represented by the quantum computer, and on the top we have the algorithms. So the focus of this work is the software in between. So what we call quantum computing platforms, which could include abstractions, intermediate representation, compiler, everything that is in between, which is needed to execute the final algorithm. So this is the focus of our work. So let's now introduce some basics. Let's give a brief overview of a typical quantum programming workflow. So here I'll give an example with one of these platforms, one of the most popular, which is called Qiskit. It's been backed by IBM. So what we do typically in a typical workflow, we define our program in a high-level API in Qiskit, which is then mapped into the hardware thanks to the compiler embedded in these platforms. And then it becomes something like this, which is called a quantum circuit or program. So let's have a look at this diagram and understand it a bit better. So it is usually read from left to right, like a musical score. We have multiple lines. Each line is a qubit, so a single piece of information on which we do our computation. And then we have these boxes, which are the operation that we perform either on a single qubit or on multiple qubits, like these vertical lines. Then another important factor is that at the end of this circuit or program, we have measurements. And measurements are the bridge between the quantum information and the classical information. In a measurement, we collapse the quantum information into a classical information, so into either a 0 or a 1. Then one of the key distinguishing factors of quantum computing is the fact that it is probabilistic in nature, meaning that if we run this program multiple times, we might end up with different measurements at the end. And these different measurements are represented by a distribution of possible outcome. So the solution here is to run typically we run the program multiple times, and we come up with a frequency histograms like the following here. So let's just remember that the output of a quantum program is inherently probabilistic. Therefore, we need to deal with distributions. So it's not as easy as in classical programs. So these are the basics which are needed for my talk. So I will go forward, introducing the methodology of our talk. Before that, I want to introduce the research question behind our study. So it's an empirical study. We are interested in looking at a quantum stack. We have on the bottom the physical layer, on top the quantum algorithm, like we saw before. On the left, we have what is considered a quantum software stack. On the right side, we have the classical part, which interplays with this quantum software. And our focus are the quantum computing platform here. As I said before, we could have intermediate representation, compiler, also abstractions, and as building blocks as well. So the first research question is to understand whether the bugs that we see in this platform, how many of those are quantum specific? So refer to this realm instead of classical software, to which we are already familiar. So the second research question is where this bug happened inside the components of this platform. So as we said, we have multiple components, so we want to better pin down which components are the most faulty in this case. Then third, we want to investigate how this bug manifests these platforms. Fourth, once we have this overview on this key characteristic of the bugs, we want to try to abstract and identify higher level patterns. So one question is, which recurrent pattern is there? And finally, we also want to give an overview of the complexity of the bug fixes of this bug. So how complex is to fix one of them? So now, in terms of methodology, I want to introduce how we selected the quantum computing platforms which are subjects of our study. So we got inspired by the list of quantum full stack libraries given by the Quantum Open Source Foundation. And we compiled a list of 18 repositories, including the most popular, like I said in the beginning, Qiskit. Then we also have Cirque from Google and other representatives also from academia. So for us, a quantum computing platform is essentially a software which is involved in the execution of a quantum program. So starting from this pool of platforms, we went through their commit history, and we looked at likely bug fix commits to start our empirical study. And to do that, we looked for the fix keyword into the commit message. And second, we also wanted to have a deeper understanding of what was going on for these specific bugs that we were inspecting. Therefore, we required to have a related issue or pull request to better explain what was the root cause of the bug or how to fix it, for example. So from this pool of possible bug fixes to inspect, we sampled 20 for each of these 18 repositories, and we manually inspected them. And we came up with more than 200 real bugs to include in our study. So our study is based on these 223 real bugs. So let's now address the question that I just introduced before as part of the result and the outcome of this work. So the first research question is, how many bugs are quantum specific? And to do so, we have to define what do we mean by quantum specific. So first, we want that we have to look at where the bug happens. And one requirement is that the mistake should happen in handling quantum specific concept. And second, we have to look at how to fix it. And the fix should require knowledge from quantum programming domain. So let's be concrete now, and let's see two examples together. So on the left side here, we can see a classical bug where there is a problem in the usage of a typical Python API that has attributes here, where the two arguments are basically swapped. And if you look at it, there is nothing really quantum in this code. It's just a bug, it was fixed, and that's it. And on the other side, we have another example of bugs, which is coming from Mythic library. And here we have a procedure which is called zero noise extrapolation, where we have our initial quantum program, and we want to add some noisy operation at the end. We add them with the goal to estimate the condition of zero noise. So we artificially add them to have a better estimate of how the program should behave with zero noise. And to do so, we have to keep track of how many operations we add at the end. And here the problem is related to the wrong way to keep track of this number. So here there was an incorrect numerical expression which was fixed. And to be fixed, you of course need to spot it. And we argued it would satisfy the description that we just gave of quantum specific bug. So let's move to the result. So how many of those are quantum? And this is the result. So we have that almost 40% of these bugs, so a consistent portion, are quantum specific bugs. And this calls and motivates further effort in quantum software engineering research. Then on the flip side, it's also encouraging to see that the rest, so 60% of them, are still classical, therefore opening up the opportunity to reuse existing techniques that could play an important role as well. Now let's move on where this bug happened. So to do so, we have to compile and aggregate, create a taxonomy of components along this platform that we analyzed. So we created a taxonomy of macro components. And this is the result. So we have 4 macro components. The first one is related, it's called quantum programming languages. And this component is related with abstractions at different levels. We have quantum, classical abstractions, and also domain-specific abstractions. Then we have the central block is the compilation block, where we have intermediate representation, optimization, and also machine code generation. On the other side, on the left side, we have everything that is related with the execution of this program, which, for example, the interface to a quantum computer. So at the end, our platform, if it wants to execute on an external quantum computer that has to interface to the cloud typically. Second, there could be simulator inside this platform, which is used to run this program. And then third, whenever we want to perform some measurement or quantum, also in other words, quantum state evaluation, we have this other category. And this is, for example, to calibrate the measurement. There are some procedures inside this platform which are devoted to this. Then on the bottom part, we have more auxiliary components like related to testing or visualizing the input, which in this case are distribution sometimes, or even the circuit that you saw in the beginning. So there is a bunch of plotting things. And then there is also infrastructural glue code, let's say. So now let's look at the results. So now for each of these components, which in total are 12, we compute how many classical and quantum bugs are there for each component. And this is the result. So on the horizontal line, we have the different components. On the vertical axis, we have the how many classical or quantum bugs we have. And here, what we can observe is that the large majority of these bugs happen in inner components, namely also, for example, quantum abstractions. So this, for us, is an insight that perhaps at this stage, running on a real quantum computer to find bugs is maybe not needed. Maybe we can still use simulators to find bugs, because even simulator can exercise this part of the platforms. Then another observation that we can derive from this diagram is that we have these two other components which are traditional, and they are affected mostly by classical bugs. And here, the insight that we gather is that perhaps in this field, where not all experts are software engineers by training, there might be the need for more core software engineering skill, or maybe better support from the community on this side. And another observation on the same diagram, in the middle, you can see that the optimization component that has a large majority of quantum-specific bugs, making it a good candidate if you want to develop, if you want to look for quantum-specific bugs. This could be a good target for your, for example, bug-finding approach. So let's now look at how can we spot these bugs in the first place. So what we did, we compiled and we break down our analyzed bugs in a traditional division between functional and non-functional. And functional was recursively split into application-specific and generics. So these are the different subcategories that we identified. And we also assigned a number of bugs for each category that we found. And here, the observation is that we can see 92 crashes and incorrect output, 77. They are the two largest and most common symptoms for these bugs that we have analyzed. Therefore, making, for example, the crashing signal a good candidate to cover many bugs in these platforms. Now, let's still look at how the bug manifests, but looking at the type of quantum and classical bugs which manifest in these two biggest categories, so the incorrect output and the crash. And what we see is that in the incorrect output, we have the highest, the majority, which is quantum specific. And here again, if we recall the introduction, we have that the output of a quantum program is a distribution. Therefore, it makes sense that interpreting this output is more difficult, and it's inherently quantum rather than classical. And this calls for dedicated testing techniques in particular, that can focus on these distribution differences, like comparing what we get with what we expect to get. And there has been previous work, I want just to mention here, QDIF, which was published last year at ASC as a reference. Then, now that we have a better look at how this bug, where they're located, how they manifest, now I want to try to identify patterns in these bugs. So what we looked at, the kind of information that we analyzed, are the following. So we looked at the actual code change that we could gather from the bug fix commit, the commit message, which was, again, informative about the bug, and also the associated developer discussion in the form of associated issue or pull request. So gathering all of this, we could form an opinion on which are the common bug patterns. And we compiled a taxonomy of bug patterns, including 4 major categories, macro categories. We have API-related bugs, incorrect application logic bugs, math-related bugs, and also others to include all the rest. And here, it's encouraging to see that we have also some well-known bugs, like API misuse bugs, or also type problem bugs. So this is good. This makes us be positive in the sense that we could reuse some existing approaches even in this domain, particularly in quantum computing platform, which is the subject of this empirical study. Then we also found something new, so qubit-related bugs, like the following. So we have incorrect qubit count as bug pattern, incorrect qubit order. Also this more interesting even, bug patterns, which is most significant bit, least significant bit conventional mismatch. Because as you saw in the very beginning, we are reasoning at the bit level at this kind of time. And it's very easy to get confused between which convention we are using. And since the standardization is not very clear among platforms, there might be even misunderstanding within the same platform code. So this and this data set provides, we argue, a benchmark, we believe, for quantum-specific bug detectors and for targeting a specific bug patterns among the one that we present. Then if we break down each bug patterns, which we see here on the vertical line, we have the names of the different bug patterns. We have the number of quantum-specific and classical bugs. And what we observed in these categories that are highlighted here, we identified new quantum-specific bug patterns where the majority of these bug patterns are consist in quantum-specific bugs, opening the venue for future testing techniques which target some and few of these bugs in a very specific way, for example. So now the last research question, since we looked at the bug fix commit, we also have information about the fix of this bug. And doing so, we analyzed how complex it is to fix them in terms of how many lines of code do we need to change to fix these bugs. And here on the horizontal line, you see the number of lines of code required to fix it. So there are a large majority of 1 or 2 bugs which could be fixed with 1 or 2 lines of code. And this is also relevant because most of the automatic program repair techniques nowadays available, they're focusing on this kind of bugs. So very, say, simple to fix bugs. So 1 or 2 lines. So it's a good avenue to try to reuse existing techniques and see how well they perform. Then you see also with these 2 vertical lines, you see also the median length of these bug fixes for classical and for quantum. And what we can observe here is that there is a large portion of bugs which are very difficult to fix, require many changes, and also the average, the median length for quantum bugs is much more than the one for classical. Opening it up opportunities to try to scale up these approaches, such as automatic program repair, to larger fixes, for example, especially for quantum, which has a higher proportion of these bugs. So let's now summarize the work with I will briefly recap the implication of our study on future work. So first, with the first research question, we assessed that a consistent portion of bugs, 40%, are quantum specific, and this causes and motivates further research in this direction. Second, we found that large majority of bugs happen in components which are inside the platform, which such as quantum abstractions, and this can be exercised also with a simulator only. Therefore, we suggest that trying to use simulator is still a good way to find these bugs. Then we found that the most common symptom is a crash, making the crashing signal a good candidate to test many of these bugs. Finally, we identified new quantum-specific bug patterns, as I've presented in the taxonomy, which is available also in the paper, more in details. And this calls for opportunities of testing techniques which are specifically focused on some of them, which we didn't know before, for example. We didn't target as much before. Then in terms of complexity, many of these bugs can be fixed with 1 or 2 lines, making it a good avenue to try and reuse existing techniques. So to link the two things. So reuse automatic problem repairs, for example. So that's it. So I introduced you the motivation, the methodology. We went through the research question, and finally the implication for future work. You are free to have a look at the dataset, which is available through this URL or this QR code. And thanks a lot for your attention. Happy to take your question and feedback, and thanks a lot.
Thank you. We have time for questions. Yes, there.
Hi, interesting talk. So I had two quick questions. So the first one of the new quantum bug classes you mentioned was most significant bit, least significant bit. So to make some understanding that correctly, is that about like, let's say I have, I want to encode maybe an integer for like a quantum algorithm, and like the way that that's being encoded as qubits during the compilation process, or is this something different?
Yeah, it's whenever you want to encode a number, for example, you want to know what the first bit. So in the picture that I introduced in the beginning, the topmost should be the most significant digits, and the letter should be the least significant. So that is exactly.
Okay, I guess. So is that problem any different than most significant bit, least significant bit in the classical case, or could you like use the same techniques for that?
I think there are many analogies, and one of the reason why it's more common in this kind of platforms than maybe in classical software is that we still don't have a clear standardization, for example, in these platforms, and even developers with each other, they get confused maybe. And an additional factor is that trivially, when you start using one of the most popular Qiskit, you have the drawings that I showed you, the circuit, where the topmost for you might be the 0, 1. But when you see it printed down as output of the computation, you have a string where the first digit that you see is actually the last line. So it is even confusing sometimes in the same platform while debugging. So I think
No, that's actually a good point. Like I do quantum stuff, and I never actually thought about the fact that those different representations could get confusing. So that makes a lot of sense. I had one other question. What kinds of when it came to quantum abstractions, what kinds of issues were people running into with that?
Yeah, for example, I'm thinking about a proper example. So let me pick from the backup. There should be a slide about additional bugs.
Okay.
Yeah, like this kind of other quantum-specific bug. We label it as an overlooked corner case. And here, this term is a Pauli term, which is specific of the quantum domain. So it's an abstraction created purposely for this. And here we have that, as you see, the change was deeply checking some types inside the platform to properly do this operation in particular.
All right, thanks. That is a good. I guess that kind of explains. Like, so I guess another thing that might be nice then is if it kind of worked towards having like some more like general purpose libraries for dealing with these abstractions. I guess.
Sorry, what's the question?
Do you think it would be? I guess that might mean that maybe it'd be good to like work towards having some more general purpose like libraries for dealing with these kinds of abstractions, maybe. So, like in the classical case, like if I wanted to do like certain kinds of analysis, like there might be like a library that's already made for the certain kinds of abstractions I want to use. Whereas it looks like in this example, they're kind of doing something a bit more ad hoc just for the compiler. So maybe more standardization there might also be good.
Oh, okay. More standardization in this kind of side, yeah, it would benefit definitely. Yeah, thanks for the question.
So I want to understand more about how you know that these bugs were found. So you have this advice on your last slide. Maybe we don't need a simulator because the bugs we're finding them in the abstractions and so on. But I'm thinking, like a bug like this, how did they find this bug if not through simulation? Or I'm just wondering how you can draw the conclusion that we don't need to worry about really running these things if you're not entirely sure how they found the bugs in the first place. Just because it isn't in the simulator, or it doesn't happen with the distribution, doesn't mean that they didn't find the bug because they were running the code.
So I'm not saying not to run the code. I'm saying to run it in a simulator. Is it what you?
Sure, but you're limited in scope. If you run it in simulator, then there's only a certain amount of fidelity that you're going to get. There's only a certain number of qubits before you run into scalability problems compared to running it on real hardware.
Yeah, that's true. So on the flip side, we have done some work on testing this platform as well. So the QDIF approach, which I mentioned, they run on real quantum computer. So they have even worse problem that they have to run with even lower qubit than what we could simulate at some point. And many of the problems they find, they are hardware related to hardware instabilities. So we'd rather focus on the software at this stage. So that's our point, rather than trying to debug why there is such a high error rate in the
So you
hardware.
have pretty good confidence that these bugs would be found just through simulation, that they're not going to capture those additional infidelities.
Yeah. That's our intuition,
Okay.
of course. Yeah.
Okay, thanks.
Thank you.
Hi, thanks for the talk. You had the figure where approximately 40% of the bugs were quantum specific. And to understand this figure, I wanted to get a sense of how much of the code was quantum specific. For example, if 40% of the bugs were occurring in 10% of the code, it would be meaningful compared to 40% occurring in 40% of the code. Do you have any thoughts on that data?
We have some breakdown by components, and that was the best we could do in terms of try to assign each bug to part of the code, but we don't have the actual number of lines per component. That would be interesting, but sometimes also, because what we did was to look at a bug and try to pin down to a specific component, that's an operation, whereas what you would require is each line of code should be pinpointed to a specific component, which is even more complex and demanding in terms of manual inspection, right? So does it answer?
Yeah, I guess. Yeah.
Thank you.
All right. Well, thank you very much, Matteo.
Thanks.